This is the fourth video in the video series about the different types of force problems that we could encounter in this unit, dealing with forces and accelerations and trying to calculate them. This is the third one that I did that was called multiple forces with multiple objects. And as it turns out, the second half of this had some friction in there. So I actually wanted to just start off with this and go from there. So we're going to need some of these numbers here, possibly in a little bit. So I'm just going to lay mine off to the side. You may want to take a quick picture of this, and then we'll have some of these numbers to look at. So for right now, I'm just going to pull this off to the side so I get another piece of paper, and we'll see what happens. Now looking at this problem, right, if I had friction in, there's going to be friction on 3 different places, and they're going to be different amounts of friction. Probably, possibly, it kind of depends upon, what that force of friction really depends upon. We'll get to that here in just a moment. The overall force is pulling to the left, so the net force in all of these is going to be to the left. And since the net force is to the left, friction is going to pull to the right. So each of these has a force of friction going backwards, right? They're FF1, FF2, and FF3. So 3 different forces of friction. So what are those forces of friction going to depend upon? That's what we just kind of alluded to here in a little bit. Well, the force of friction formula says force of friction is less than or equal to this mu times the normal force. And mu is either, it's called a mu sub k, the coefficient of kinetic friction if the object's already moving, or an Fs, which is the force of static friction, or the mu of static friction, which means the object's just getting ready to move. And we're assuming these things are already moving before they hit this frictional spot, so we're going to have a mu k. So this mu could either be the object sitting there or the object's already moving. In terms of the math, it makes no difference in terms of how we use the formula, but it makes a difference in terms of just the overall motion of the object. So what we need to do is find those 3 forces of friction. All right, so the normal force for all of them is the same as the force of gravity. We talked about that on the last video, but if you didn't watch the last video, we'll highlight that real quickly. Since the surface is exactly horizontal, and this works for all surfaces exactly horizontal, these objects are not going to be accelerating upward and downward, which means the upward and downward forces have to cancel. If they're not accelerating, the net force is 0, which means the acceleration is 0. So for each one of these, I can type in this mu number, 0.22, times their mass. For the first one is 3.4, so this is force of friction 1, kilograms times 9.8 meters per second squared, the acceleration of gravity. Not just gravity, the way some of you want to shorten it, the acceleration of gravity. So if we take 0.22 times 3.4 times 9.8, our result is 7.3 newtons. Now this is a good time to talk about this less than or equal sign. I alluded to that in the last video that we'd spend a few minutes talking about that. The force of friction here is going to be less than or equal this number. If the object is just sitting there, right, and I only pull with a force of 3 newtons, this force of friction is actually not 7.3 newtons, it's only 3 newtons. If I pull with 4 newtons, force of friction is 4 newtons, and so on and so forth, until a force I'm applying is equal to or greater than this. So if it's just 7.3 newtons, once again, the force of friction is just 7.3 newtons. But as soon as I start pulling with, say, 7.4, 7.5 newtons, friction is 7.3 newtons. If I pull with 800 newtons, force of friction is still 7.3 newtons. Friction equalizes out up until a point, and then it stays the number that is given by this equation. Right? So, as we saw earlier, the tension forces and the applied forces and all these boxes, let me slide back up. If you weren't here, as I said, this was at the beginning of the video, all of these are greater than the 7 newtons. All these net forces to begin with are bigger than that. So this is going to be 7.3 newtons. That is going to be our force of friction number we'll use, at least on this first object. Right? On the second object, it's going to be 0.22. 2.1 is the mass times 9.8. So 0.22 times 2.1 times 9.8. Sorry. Calculator issues again. 2.1 times 9.8. Try this again. Here we go. 4.5. So my calculator is going, you do want to double check my math and all of these. And if you end up with a slightly different number, go ahead and use that number as you go through the rest of the problem. And then talk to me about it later, and we'll actually, maybe I'll double check and see if who's correct. But I think these are correct at this point. Both of these are going to be 7.3 newtons because both of these objects had the same mass. So now these are my forces of friction. So the question is, how does that change anything that we did before with all of the net force equations? And what it's going to do is it's going to add another term to these net forces. Because before, on the first object, right, we just had the friction, the applied force going forward and the FT1 pulling back. Well, now we have the tension, wow, I got to slow down. We have the 34 newtons pulling forward, the tension 1 pulling back. Now we have the force of friction pulling backward also. So we're going to add into this a minus FF1. And on the second object, same sort of thing. We have the tension 1 pulling forward, tension 2 pulling backward, minus FF2, force of friction on the second one. And on the third one, now we have this tension force, second tension force pulling forward. We have the force of friction pulling back. So we'll have this minus FF3. And so it makes our equations a little bit longer. So let me see if I can go ahead and do that. However, I think I just want to add it to the ones over here on the right where we've already got some numbers and some math in there. So this is going to be minus the first force of friction, minus the second force of friction, and minus the third force of friction. And we have numbers for those. So let's see if I can kind of leave both of these up here together and see. I don't think I'm going to be able to rewrite them there. So I'll slide this all the way off. You just have to look at your other, and actually I'm going to slide down. We'll get to some brand new paper here. So if you'll need to, you might have to go back to this, take a picture of the other thing too, so you have them kind of together, and you'll see where these all work. So for our first one, it was 3.4A equals 34. That was our original force pulling it forward, minus the first tension force, minus 7.3 newtons. That's our first force of friction. For the second object, 2.1 times the acceleration is that first tension pulling forward, the second tension pulling backward, and its force of friction pulling backward. Sorry, I'm just going to get rid of these units again. When I'm doing the math, it's easier if I don't have the units in there, as long as you remember that they are there, right, and can take care of them later. And for this one, it was 3.4 times the acceleration. Before we had our second tension pulling forward, but we also now have this 7.3 newtons of friction pulling backward. However, we have exactly the same situation as before, where we have 3 equations and 3 unknowns. We just have other numbers now that we need to deal with. So once again, I can solve this equation for the second tension and put it in for the second tension, solve this entire equation for the first tension, put it in for the first tension, and then go back and rework all of the math, get our accelerations. Once we have our accelerations, put them back all in all of these equations, and come up with all of the tensions and all of the net forces. I'm not really going to work through all of that math here. I'm going to pause the video for a moment, work through the math, and just plug them, and then give you my final answers. And if your answers don't match, once again, you can have a quick conversation with me, but this is the process. From here, it's just algebra, and I don't think I want to spend another 8 minutes working through the algebra live with you. I will just work through the algebra. I'll write down the equations and put them up here. So I'll be back in just a moment, and everything will be written right here, and you can see how I did the math. So let me pause this for just a moment. Okay, so this is the result of the math and the algebra. So I'll just kind of highlight a couple of things real quickly. So what I did is I went back up into this bottom equation. I started here, right, and put in the, solve this for the second tension. There we go. And then I put that into equation 2, which is up above. So this is where this tension 2 was in the equation up above. And I did the algebra, collected all the like terms, came up with this for the first tension, put that up into the first equation up above, right? And that's where the first tension was in the equation up above. Once again, did all the algebra, collected all the like terms, did all of that, and got the acceleration as 1.674 meters per second squared. This time I left out all of the sig figs in a little bit more detail. So then just put that acceleration number back up into all of the equations, did all of the force calculations, and ended up with these results. So I will go ahead and let you double check all of the math. I believe these should all be what they are. You know, once again, leaving that acceleration number out a little bit further this time than I did in the last video. They worked out a little bit more carefully. So once again, take a look at them. If you have any questions, you can ask, but that should be how these equations work. Thanks for watching.